So, in this vodcast, we're going to look at a particularly useful type of star called Cepheid, or I prefer Cepheid variables. Okay, so this is part 3 of stellar characteristics and evolution. And the IB tells us we have to understand Cepheid variables, we have to describe the reason for the variation of Cepheid variables, and we have to determine distance using data on Cepheid variables. Interestingly, although it tells us we have to know about determining distance, but I don't think we have to know in great detail because it doesn't give a data booklet equation. Until we actually get a few exams under our belt, we're not going to really find that out. So last class, I introduced you to the instability strip. The instability strip, stars within this region can be variable. Main sequence stars, not always, but there are some. But if you get above the main sequence into giants and bright giants of this particular class, then you will find that they are definitely very variable stars. The process by which they vary, it says you need to know it, but I don't think you need to know it in a huge amount of detail. But basically, if you think about helium, helium in its natural state has 2 protons, that makes it helium, and two neutrons normally, but what we also care about is the 2 electrons. If you ionize helium, it's only got 1 electron, and doubly ionized helium has 0 electrons. These differ in how they absorb and what percentage of radiation from the sun, from the star, that they can absorb. So doubly ionized helium below the photosphere absorbs a great amount of energy. Therefore, the outside layers of the star get very hot and expand. As they expand, they get cool. This allows some of the electrons to recombine with the helium, which means it's no longer doubly ionized helium, it's singly ionized helium. And singly ionized helium doesn't trap radiation in the same way, so the star is able to cool down. As it cools down, it shrinks. Okay, it's no longer absorbing the same amount of energy. But as it shrinks again, it gets hotter, which leads to greater ionization, which leads to greater energy absorption, which makes it expand. And the process continues. As the temperature of the star, as the Earth's surface area of the star varies, the temperature varies. And as the temperature varies, the luminosity varies. It's all some weird feedback loop. And this diagram, this animation tries to illustrate that. So the higher outward pressure caused by this helium heating, which was first described by Eddington in the 1920s, the star genuinely physically changes temperature and pressure. And here you can see a sort of screenshots in a distant galaxy showing this process happening for a star. Now, this is actually quite interesting because one of the advantages, one of the nice things about these Cepheid variables is, going back over here, is that they are very luminous stars. Here's our sun down here. These things are orders of magnitude brighter. So you can see them through very great distances. Okay, we're using a powerful telescope here, but still, this is a star in another galaxy that we are seeing, an individual star. And the great thing about Cepheid variables, why we absolutely love Cepheid variables, is because if you know the period, T, this is T period, not temperature, I apologize for the confusion, but if you know the period of the star, which is the time taken between 2 points of, equal on the star's variability chart, if you know that period, then you know the luminosity. There is a very clear relationship. There are actually a couple of different types of Cepheid, let alone other related stars, and they have slightly different formulae, but still, from their light curve, from their spectrum, you can tell what type it is. And once you've identified the type, you measure the period, which is between about 2 or 3 to 30 or so days, and you know the luminosity. So take light curve of the star, determine which type of variable star it is, apply the period luminosity relationship that's valid. That will give you the luminosity. And as we previously saw when using spectroscopic parallax, if you know the luminosity and you know the brightness, these can be combined by this formula, and therefore you can work out the distance to a star. This is also combined with the fact that Cepheid variables, as I said, are really, really, really bright. So you're not just measuring the distance to a star. If we apply this relationship to this particular Cepheid variable, we're finding the distance of galaxy M100. And this allows Cepheid variables to act as a standard candle, a very, very powerful standard candle for measuring distance. And we can use close by Cepheid variables against parallax and calibrate our system that way. And distant Cepheid variables we compare to things like redshift and calibrate our measurement scales in that direction. Thank you.